Yeah, absolutely. I was just going to say, please interrupt and ask questions at any point. I definitely, in the conclusion, I very much welcome either questions or comments. I put some things in the conclusion that I wasn't certain of, so I would welcome the people who know more about it than I to help me out there. So starting off, I'm going to talk about gauge theory, in particular things on the lattice, so in a condensed matter standpoint, and then I'm going to talk about specifically the toric code and fractons, two systems that have been around either for some time or have been kind of one of the rising things in the last few years. So the table of contents, I'm not sure what's going on with section 2 there, but first I'm going to talk about the toric code and the motivation for it and where it comes from. Next, I'm going to talk about how we can recover the toric code from a gauging procedure, notably going from the transverse Ising model to the toric code via a few gauging steps. Next, I'm going to do a similar thing that I did for the toric code, describe some of the dynamics and what exactly the x-cube model of the fractons are. And then I'm going to do a similar thing from a matter theory on a lattice, and I'm going to gauge it very similar to how I went from the transverse Ising model to the toric code, but now with the x-cube model. And then as a conclusion, I'll do some future directions which are kind of motivated by work going on or went on in the past at Stony Brook, actually. So starting off, I will start with the toric code. And the motivation for it was kind of taking, during this revolution of quantum computation in the late 90s where Shor and stabilizer codes were, this was really right at the beginning of stabilizer codes with fault tolerance in quantum computation. And the idea was to sort of go from pure quantum information type of things and go on to condensed matter. And so putting things on the lattice, what Kitaev did was he made kind of, I believe he calls it like a penalty function, so that when local interactions are present and they act in the system, it's kind of like violating energy, because if you use or if a local interaction happens, energy is lost. And so what his scheme was, which we'll see in the toric code Hamiltonian in just a second, was to make a Hamiltonian and try to find the minimal, like the ground state of it. So if local interactions violate the stabilizer terms, then costing energy would not be in the ground state. And so this was the first paper that Kitaev wrote on the archive in 1997. And soon after that, it was realized how topological things were. And Preskill, Kitaev, and many, many others started to look at this from a condensed matter standpoint, where they looked at lattice gauge theory from all the way back in the 90s with Susskind and Cugat, where they started to look at lattice models and think about some of the things that were protected and some of the things that, like, for instance, topologically protected ground state degeneracy and things like that, and why what we can use from condensed matter in the quantum information side of things. So the Hamiltonian for the toric code looks like this. So this is the original Hamiltonian from Kitaev's model, where he has terms where these little things on the edges are gauge fields, and these vertices are where on the lattice where it intersects, and these plaquette terms are kind of squares that surround each of a gauge field. At the moment, it's not really a gauge field. I kind of jumped the gun there. At the moment, these are just qubits. These are Z2 degrees of freedom, up or down. And so these terms here around a vertex and around a plaquette are defined as follows. It'll make why I call that a gauge field will make a little bit more sense when I get to that. And the first thing you would like to look at, based on Kitaev's scheme, which was that the local interactions of a Hamiltonian cost energy, and so we would like to minimize the energy, in quotes there, of the Hamiltonian, and find where that, the idea is to keep it in the ground state so that errors don't occur, quantum errors and error correction. And so if we were to look at the ground state and we envision kind of unoccupied qubits or excitations as blue, so here I'm going to say, because we see these things as a spin 2, we can envision them as kind of Pauli matrices, where we know that the eigenvalues of Pauli matrices are either plus or minus 1. And so if we were to identify plus 1 as being the ground state, we can kind of come up with different ways in which the ground state can be achieved. We can either have 1 and 1, we could have -1 and -1, or -1 and 1. And these are different ways that you can come up with the ground state in these various excitations, with the not thinking about vertex or plaquette operators for the moment, but just about how an intersection or a crossroad is traversed. And the reason this is significant is because we don't see in any of these circumstances anything where it stops at a particular point. So for instance, if I come in, I'm going out and going out and going out. There's no kind of coming in and one of these is left, either unoccupied or occupied. And so what we can envision that as is that loops are what is preferential in this model up here. So loops are what is energetically preferred to keep things in the ground state. And things get even weirder if we were to identify the boundaries of this theory, and that's where the topology of the next few years after this toric code come in. Because if we were to put things on a lattice, we can start to talk about the ground state degeneracy and how degenerate a particular. I'm trying to figure out how to get this. Here we go. So maybe up or down? No. Let's see here. Maybe like that, and then I'll just click on manually.
You wanted the full screen?
Yeah. So I think maybe I'll just use these little buttons down here from the LaTeX Beamer file. Okay, sorry about that. So once we put things on a torus, things become, you can think about what unique setups there are for the ground state. And it turns out there are kind of different universes. So you can have, because the torus has non-contractible loops that you can make, these loops are energetically preferred, and they are all the ground state, and they're distinct. If I have this loop here, there's no way that I can contract this loop down to here with, for instance, these plaquette operators. Whereas, if I had two stripes in this kind of longitudinal direction here, I could use the plaquette operator, because what the plaquette operator would do would be to turn the occupied states into unoccupied states. And I can just keep applying this plaquette here, plaquette here, plaquette here, and that's why you're only seeing one particular line. Because if I had two, it would turn out that that would be dual to this kind of universe over here. And so that's why you have one, I guess this would more be the transverse direction, and this would be the longitudinal direction, or you can have one in each. And so now you're starting to see where this topological stuff comes in, and moreover, this degeneracy is what's called topological. And by that, there are many definitions of it, but the definition that I encountered the most was that when you perturb it by, for instance, let's apply a particular tau operator. Let's just say you would take one of those ground states from before and apply a tau z or a tau x to it. As you take like a thermodynamic limit or something like that, the perturbation becomes exponentially small, and so that's saying that this kind of gap on the ground state is protected. And so you have this, which we'll get to a little later in the X cube. There's this kind of so-called passive protection or passive error correction, where you don't need to explicitly do anything, you can let the system find its ground state, and that's your error correction. So that's the system. That's kind of the dynamics of the toric code. But what I focused mainly on in this semester was gauging and how I can go from one system to another system. Because, a priori, when I first started, this toric code and X-cube model were, they felt very ad hoc to me. I didn't know where they were coming from. Whereas taking like an Ising model, that felt, more like StatMech or, something that I could wrap my head around. So going through the procedure of gauging is what I focused mostly on. And so starting with our good old, I scrolled again. Starting with like a transverse Ising model where you have matter fields on each of your lattices or on each of your vertices. So for instance, let's say vertex is represented by V or W. There we go. I can have an Ising coupling term between each of these matter fields on the vertices, and I can also have a transverse field. For simplicity, I'm just going to let the transverse field be uniform throughout all of it and just set it equal to 1. So that's why I'm making this identification here. And the first step in gauging is to introduce gauge fields in the theory. In this theory, it's a little bit easier to guess. We'll encounter, it's a little bit hard to know where to place your gauge fields in the X-cube model, but in the toric code, looking at what the system looks like, it's kind of clear that if in the Ising model your matter field is on the vertices, it's kind of there's only really one option, and your option is to place the gauge fields on the edges. So I'm going to place gauge fields between each of the matter fields. And so the first thing that this alters is my Ising coupling term. Between each of the matter fields, I now have a gauge field. So my tau will be a gauge field, and my sigma will be a matter field. The next thing I do in gauging is to enforce something called local symmetry, or you can also kind of envision it as like a Gauss's law. If I were to integrate around a particular vertex, that should tell me, like in Gauss's law, how much charge is enclosed by that integration surface. So for instance, if I'm integrating around these gauge fields, it should tell me the charge on the matter field at the particular vertex. So my AV term, like this, is going to be represented by one of the matter fields and a product of the 4 gauge fields that I'm integrating around. Also, I'm going to enforce no flux condition. So there's no kind of like in, you can see that a lot of these terms are coming from electromagnetism, which I'll get to in this conclusion over here. But this no flux condition is that I'm integrating around a particular loop. I should have nothing going, in any particular direction. And I'm going to represent this by the 4 matter fields in this, kind of shaded region here. But what ends up happening is, because these matter fields are represented by Pauli matrices, each of them squared with each other just end up giving 1. And so now I'm already at the point where I'm recognizing something from the toric code, because the toric code, just 4 things around a particular vertex, green, 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 and green, was the second term. At the moment, this AV isn't quite there. So the next step I have to do is to what's called integrate out the matter fields. This is something that...
Can I ask you a question? Can you go back to that? Your AV, the part that's involved is different from your convention, sigma and C. Is there a reason that you choose this?
Let's see, you say this should be a sigma Z?
No, in your previous toric code,
mm-hmm.
you're using the Z as a vertex, and then plug it as a tau x, right?
Yes, let's see.
And there you're switching.
Oh, I see what you mean.
Okay.
Yes. So
at the end, when you after integrating the matter field, you would have a slightly different. You would switch the x and z.
Right. I don't think it matters. I think.
Yeah, it doesn't matter. Just the convention.
Okay. Yeah, it's because of the like each of those things would anti-commute. So.
Tau z and x anti-commute, but z and sigma they commute. Right?
Yes. I think it's completely convention, but you're right. I did.
So I'm just asking that when you integrate out, the Hamiltonian you get would be in the different convention.
Yes. Yep.
Okay.
And so once
again this equation there, you say the BP. How do you get the BP? What exactly are you taking product? The I in plaquette. I is for the sigma, it's on the vertices.
Yes.
And for the I, for the tau,
it's like the edges in the. So I guess in general, like this P would be the shaded region. So this for this term, for instance, would be the 4 matter fields in this shaded region P, and here it would be the 4 gauge fields in the shaded region P.
And how do you get the sigma z to the 4th power? They're at different locations, right?
Yes, they are at different locations. But when I'm making this term, it would ultimately be, sigma 1, sigma 2, sigma 3, sigma 4, but they're all the same, like sigma z operator. So it would be like sigma z to the 4th. At least that's what I was reading in the papers. Like I think in doing so, you would just be multiplying 4 sigmas and 4 taus. And so that's why I made this kind of identification right from the start, because I can immediately see that this is just like what I had in the toric code, like there. Except, yeah, you're right, this was a Z.
Okay.
So this would be the same, like if I had kept the convention straight, that would be an X and that would be a Z, and then the product of the 4 of them around a plaquette would be what I had there.
So in a sense, are you trying to integrate to get the BP, or?
When you say trying to integrate, what does that mean?
Yeah, because I understand you're saying that the sigma z, if it's the same sigma z to the 4th power or squares identity, but they're located at 4 different locations.
Yeah, that's a good point. I didn't think about that. I didn't think that the operators being at different points.
Get this argument from? Maybe it's could you go back and trace back that argument? Not at this moment, but
yeah, absolutely,
later.
Absolutely. I think the only I could find out where this is coming from, but that's a good point. I didn't think about if an operator is at a particular location, I didn't know that does anything to it's algebra or anything like that.
I thought that you were imposing just to give some dynamics to the gauge field. That's the gauge field term.
Yeah. Yeah, and then this would be like the local.
Maybe that has nothing to do with the matter field, just for the BP. But the only coupling would be the matter field through some kind of minimum coupling, which is what you write.
Yeah.
Sigma x and tau x.
I think you might be right. I think I may be reading into this too much, because the only thing that I took in the literature was really the bottom 2 equalities here. It wasn't. I just kind of inferred. So that may have been a mistake on my part, that the full term was all of these.
Is there by any chance like condition, like relation between sigma and tau, like the difference between sigma is tau or something? Because like in lattice gauge theory, we take like the h degree of freedom is like how do you say like g times g inverse or something like that, right? So I was guessing like tau is related to adjacent sigmas by sigma times sigma inverse or something.
Oh, okay.
It could be tau z. There's one on the left, sigma z on the right, also another sigma z from another.
Yeah, like from over here.
Vertex, and then you have, because you are placing it on the plaquette, and each appear twice.
Yeah.
So sigma z square is identity. Does that make sense? I mean,
yeah, that makes sense to me.
A field student who is really good at field theory.
Okay, thank you. Yeah, thank you very much for pointing that out.
Yeah, maybe that's it.
And then speaking of field theory, this kind of, we still have matter fields at the moment, but in the toric code, you realize there weren't any matter fields. So the last step is to do something called integrating out the matter fields, it's kind of standard in quantum field theory when you're, want to make an effective field theory and look at a particular low energy limit. So what we do in this case, when we want to minimize a particular term that includes the matter field, this term will go to 0. However, this term, this Gauss term or local symmetry term, this will in effect go to 1, and this will stay. And moreover, one more limit that we take in this gauging procedure is to take kind of like the symmetric paramagnetic phase. So you're letting the Ising coupling go to 0 so that there's no permanent magnetization. And so we have 0, 0. This effectively goes to 1, and we have this term here, which, if we look back at what the AV term, again noting that I switched the conventions here, this was exactly what we had here. So we had the product of the 4 of them around a particular vertex, and the BP term was around a particular plaquette. And so that's the gauging procedure that goes from the transverse field Ising model to the toric code. And now, moving on to fractons, it kind of, in a fun way, started in...
Another question.
Yeah.
So is there a... Oh, yeah, you're taking the limit, I see, taking the limit Ising coupling to 0?
Yeah.
And then... essentially, you're taking the external field to infinity.
Yeah, or that way.
And then your sigma x is fixed to the plus eigenvalue. Okay. Okay. Yeah. Okay. Thanks.
So just like when we were talking about where the toric code comes from and why it started to be the case that people were looking into condensed matter, the first instance of the toric code, in general, its first iteration was with a student. I believe he was still a student at this point. His PhD thesis was in 2011 as well, where he started to look at what's called self-correcting quantum memory. And not kind of in this theoretical portion of the toric code, like we just encountered, was in 2 dimensions. People extended it to 4 dimensions, but Ha was looking at 3 dimensions. So notably, what we live in. So where we can start to, use some of this theoretical kind of topological quantum computation. He was looking at 3 dimensions. And moreover, what he was looking at was very similar to this, where we were looking at kind of finding the minimum energy of a particular system. In fact, I forgot to do the citation, but I did have it open on my browser. What's kind of viewed as, even though, fractons weren't being discussed and really the quantum information wasn't the main subject of this paper, but this is a quantum or a condensed matter paper written all the way back in 2005 that Ha cited and used as inspiration for the lattice model that he constructed, where this topological overprotection is the key word here, because the kind of gap above the ground state was so big that the main draw for him was that it would kind of do this, like what I mentioned earlier, this passive error correction on its own to such an extent that it would, like you wouldn't have to worry about some kind of physical mechanism doing your error correction for you. It was, quite some time before the community jumped on it. Like I can't see buttons down there. Okay. That here. But it was quite some time before people started to realize, Ha himself, along with collaborators, that this lattice model that he was constructing was very weird. In particular, one of the weirdest things that people, and as you can see from the Google Scholar citations, the 2012 paper or 2011 paper didn't generate a ton of attention, but as soon as this came out, things started to really ramp up. And moreover, the next slide is 2016, when this X-cube model came into play. People started to realize that a lot of the excitations and dynamics of these fracton theories were not characterized by any of the periodic table of topological insulators and things like that. Like there weren't like what is the other paradigm, like the Landau-Ginsburg theory, and we'll get to it in the conclusion. Like there was no continuum theory of quantum field theory that explained these, and one in particular, this is the fractons before they were called fractons, an excitation that is completely stationary. So as a single object, it's completely stationary and doesn't move by itself. And so this is when the condensed matter community, not even because when this was much like the Toric code when it was originally done, or Ha when he originally did it, it was of course very theoretical, but it had this huge application at the end of it, like quantum information and quantum computation. It was at this point that people started to just study it for the fun of it. Like there was this weird thing happening in these theories that he was studying, and people needed to explain it in a topological order sense and in a quantum field theory sense. And the X-cube model in particular, which again was Ha and collaborators, was where things really even took off even more, because this was dramatically simpler than this what's called the Ha's code. That was using a lot of things, which I'll talk about in the conclusion as well. Like there's a lot of polynomials and algebra that go into it, where you can see here this polynomial representation, where this X code is much, much more simple, and it represents a lot of the same things from the Toric code. And so that's why I chose to talk about the X-cube model, notably because it's so much easier to think about in terms of gauging. So let me get into the X-cube model and what it is. Now we're in 3 dimensions, and so some of our terms look a little bit different. At first, we have a gauge field. Well, at the moment, again, I jumped the gun. These aren't gauge fields; these are just Z2 qubits around a particular lattice. So here we have things around an entire cube in 3 dimensions, and then around each of the particular axes. So here, nothing is along the X, nothing is along the Z, and nothing is along the Y. And we have qubits, Z2 degrees of freedom around the other ones. One of the main features of this is that there are things called subsystem symmetries. So instead of, Lorentz symmetry permeating all of your space and time, you're kind of foliating your geometry or your space or something with different symmetries. So, for instance, you could have a rotation symmetry on your z equals 1 axis, or plane rather, and like a Lorentz boost symmetry on your z equals 2 plane. And so the reason this was so pivotal to what was happening in terms of excitations is that if you enforce various symmetries on your excitations in the theory, you have different behavior. If you have just one of your symmetries are being obeyed, you have something that can move in a plane. If you have two of your symmetries, you have what's called a lineon, we'll get to in a second. Or if you have all three symmetries being enforced, you have what's called a fracton, which cannot move, because if it were to go up a little bit into this plane, it would no longer be respecting this symmetry, and likewise for all the other symmetries. In particular, these lineons can be viewed kind of in a lower dimension as well. If we just look at a tau x operator on, let's just pick the y-axis, so we're looking at along this direction, what we can see that if we picked a particular, placing a tau x along one of these y directions, we would see that based on these in particular, because the tau x would just commute with this, so there would be no interaction. If I placed the tau x here, there's already a tau x, it would just commute. But here we have an anti-commutation, so we have 1 and 2 from the something on the zy and something on the xy, where we wouldn't get anything from this term. And so here, this lineon, it's moving along the line, but one of the things we can notice is that because it interacts with two of those terms, there are two excitations like kind of paired together with each other. What we'll see in just a second with these fractons, it would be impossible for just one of this excitation to move along a particular axis. What we'll see is that the word fracton came into play because it's kind of like a fractal nature. So at first, let me kind of give you a 3D picture before I move into like this top-down kind of formalism I made for this. Envision putting a tau z along one of the edges. So if we go back to our Hamiltonian, we see that what's going to interact with this is just this cube right here. And so if we put a tau z on one of these links right here, what would happen is that the cubes around it would get excited, because all of these cubes around it are sharing an edge. So all of those cubes around it have this term. So one gets excited, and now this whole cube is affected by the tau z on that edge. And things get even more clear when we start to increase. So first I'll do 2 and then 4. If we have 2, now we have this one is one edge is getting affected. So this is now an excited cube. This is an excited cube. However, there are two edges that interact. So now that we have a tau z interacting with that tau x and another tau z interacting with it, we're going back to its original state. So it's not excited anymore, it's kind of back to where it started, before there were any tau z's. So we've got standard, and two excited boxes along the edge. 4 is even more clear, and it starts to be the case where we can see what we mean by you can't move a fracton, you can only make copies of it. Now that we have 4 tau z's, I did away with the 3D because it was getting kind of tedious to keep making that in PowerPoint. Now I have 4 tau z's. So here again we have excited, because this will only one of the edges will be touching this tau z. Here we have 2 tau z's touching it, so it's back to its original state, unexcited. And here, likewise, it's actually back into its original state, because 4 edges just, kind of like over here, where we had these, 4 things interacting that just return the identity. So this middle is actually back to its original unexcited state. And now we have 4 excitations, what we'll coin fractons, along the edges. However, if I were to purposely try to move just this one, instead of doing things kind of symmetrically by 1, 2, 4, what if I were to just try to move this fracton? What happens? Well, I'm going to apply a tau z to maybe this one or that one or that one. But what ends up happening is I can't move this fracton without making more of them. So sure, you can envision me, okay, yeah, sure, you moved this fracton here, but you also created 2 more. So that's where this fractal nature comes from. And so if you have a fracton in excitation along one of these boxes, there's no way to move it without spawning more of them. There's only fractalizing is the way that you can, I guess you can view it as moving, but there's no way to keep the number the same and to move it. And so now we get to the fun part, which is applying what we learned from gauging the transverse Ising model to get the toric code to gauge some matter field on the lattice to get the X-cube model. So first, it's as I mentioned with the toric code, it was kind of natural to know where we would put our gauge fields based on what the toric code looked like. But in this case, instead of putting them on edges and things like that, it's actually most helpful to think about the subsystem symmetries, where you can envision how do you obey all the subsystem symmetries along 1 plane, 2 plane, 3 plane. The only way to have the equal amount is to actually put them on the plaquettes. So here I'm putting my gauge fields on the plaquettes around a particular cube. So I've got a gauge field on this edge, a gauge field on that edge, and so forth. And my matter fields are on the vertices. The next step is just like we did in gauging the transverse Ising model. I have a local, or kind of like a Gauss's law term, where I'm integrating around my gauge fields, and it's going to tell me how much charge is on my vertex with that's where my matter field is. In this case, we've got 3 dimensions. So when we're integrating around this thing, I've got the 4 quadrants of one plane, the 4 quadrants of another plane, and so forth. So I have 12 gauge fields around a single vertex. So this is what I'll call my local, or my Gauss's law constraint here. My matter field is just my matter fields on my vertices. And now for the flux, where before we were just talking about squares, in this particular case, I'll talk about directions. So if I don't want any flux in the x direction, what I'll do is just like in the, I didn't want anything coming out of the edges. Here I'll kind of envision it like a cylinder, and I don't want anything coming out of the top or the bottom of the cylinder. And so I can keep my gauge fields around this cylinder, like this, and then I don't have anything along my x-axis. So for my x no-flux term, I have gauge fields around the top, the bottom, and the sides. And that's these little abbreviations down here, top, bottom, side. This would be my x no-flux term. The top, bottom, front, and back would be my no-flux on the y direction. And then the sides, the front, and the back would be nothing along the y direction, or the z direction. So that would be my no-flux z term. And almost just like we did with the transverse field Ising model, I have to integrate out my matter fields now. However, one of the extra steps in this case is to talk about something called the dual lattice. So I'm going to shift perspectives. That's really all it is. It's just shifting where you think everything is based on where you're starting your lattice from. So the result of this is that my gauge fields that were on these plaquettes on the sides of my cube are now along the edges, just like they were, in the toric code. The things are along edges now. And so if we envision, also we're integrating out the matter fields, kind of doing two steps at once here, integrating out the matter fields for this term from the sorry about that. The matter field goes to 0, and just like with the local term in the first half of this talk, this will go to 1. So we do that here. But I'm going to make this identification that this term here, all these things around around a particular cube, I'm going to call that AC, and it's kind of mimicking my AV from the toric code up here. Likewise, I just have to remember for my no flux that now my gauge fields are along the edges. So I'm going to do it in the same way, just instead of cylinders, I'm just going to think about the axes. So now for my X no flux term, where before I had the top, bottom, and the sides, now I'm just going to worry about things on the axis. So if I don't want any X flux, I just don't have gauge fields along the X direction, and I have them along the Y and the Z. And I'm going to make a further identification to mimic the toric code again. I'm going to call these no flux terms around a particular axis. So if none of the gauge fields are on the X, I'm going to call that BV of X, where that means that all the gauge fields are on the other axis. So at this point, I have almost exactly, not almost, exactly what I started with this X cube gauge field. I have the matter, which I integrate out, so this term goes to 0. This goes to 1, and then I call this term here my AC, mimicking the AV from before, but now we're in 3 dimensions, so I have it around the cube. And then I do the same thing with my no flux terms. My no flux go from the plaquettes to the sides, to the edges. So I have my no flux along the Z, no gauge fields on the Z direction, just like we have here. No flux along the Z would be this one. No flux along the Y would be this one, right? No gauge fields here, and no gauge fields here along the X. And just to kind of write things in a summation notation to match what is commonly found in the literature, this is exactly the Hamiltonian of the X cube model, where here I was just doing things pictorially. This is the exact Hamiltonian that you would find if you looked up the toric code, you would find what I had before, and if you looked up the X cube model, this is the Hamiltonian you'd find there. So that was the bulk of what I worked on this semester, kind of learning the ins and outs of what it means to put things in matter fields and gauge fields on a lattice, and what gauging means. I want to spend some time on the conclusion because a lot of these slides in here are things that I was confused about, and I spent a lot of time looking for them, but because the objective of this semester was to kind of learn. Really, it's not none of this was original work that I was doing. So I thought I would just kind of open the floor in this section to ask questions of the audience, because I'm sure I already learned some more stuff. So at first I wanted to talk about relating the further directions to things that either in the past. Andrei Gromov is a past PhD at Stony Brook. He worked under Sasha. He did some really remarkable work, and this is where I kind of got into fractons. This was what I was working on last year. In high energy theory and gravity, it's known that you can take a Lie algebra and view it as like sort of symmetry transformations that go on in a theory, and you can do kind of a gauging procedure, which is why I was so interested in this lattice gauge theory, because it's quite different from what I learned in taking things from a Lie algebra to a gravity theory. However, one of the citations that showed up on this paper, which I was working on all year last year, was this, which was taking what's called a multipole algebra, which is an algebra formed based on the polynomial symmetries, which came from a very different context. you can see all the references on these last two slides. If you can have the slides, anytime you like, which was, constructed in a very different circumstance as well. This was I think scalar field theories. Like it was a non-relativistic quantum field theory paper about polynomial shift symmetries. And what Gromov did was make an algebra out of those polynomial shift symmetries and gauge it in, one of my main goals this semester was kind of maybe, I thought maybe he was talking about this type of gauging, because even though he cited this paper, what I was reading in this paper was very different from what I encountered. So maybe it was a different community and what gauging means. And so it's much more similar to what I did this semester, but I'm still finding myself definitely needing to learn the polynomial formalism, which from Ha's original code was much more prevalent versus like the kind of X cube model, which was more lattice condensed matter focused. And also I wanted to highlight that this kind of polynomial formalism of fractons was the subject of a previous master's student thesis of Professor Wei's. Let's see. Where it was kind of looking at like RG flows in models like this, where most of it relied heavily on this kind of polynomial formalism. And you'll see that I highlighted this thing called tensor gauge theory. It is kind of this upgrade into thinking about things in higher forms, in like a differential form language. And I wanted to highlight that because it's kind of something that relates both of these two further directions. And the reason I point out this further direction is Tzu-Chieh Wei, I believe, is coming to Stony Brook in the fall. He's currently a postdoc at Princeton Institute of Advanced Study, and based on a lot of his work with Natty Seiberg, which was trying to fit these fractons into like continuum quantum field theory language, because at first it was like nothing like that had ever been encountered in either condensed matter or high energy, and so that was their objective. And recently, something called higher form symmetry breaking was inspired by these Professor Xiao's work, which is in many ways, it relies on this symmetric tensor gauge theory. But one of the things, and the reason why I'm putting my, part of my talk in the conclusion here, was that I'll skip to it. Maybe it might be easier that way. One of the papers I read about this higher form symmetries in fractons, this was a particular paper by, this is a collaborator of Professor Xiao's, and it cites this first paper on higher form symmetry breaking in fractons. And one thing I noticed when I was reading it was it came up with this, maybe this is just a generic thing, and this connection I'm making is totally coincidental, but this looked like something that I encountered when I was doing this. Kind of one of the motivations for the toric code in a physical sense was something called QED on the lattice. And if I compare this term here with what I was experiencing at the very end of this section, which I'll get to right in a second, it looked similar to me. And I don't know, most of what I encountered throughout this gauging procedure was kind of, it wasn't easy, but it was also something that I could find easily in the literature. But this kind of QED on the lattice was something I struggled to find. Maybe I was looking in too many condensed matter. Maybe this is more of a particle thing, but I was, hoping to get some clarification on it. So let me, first talk about what in the, the particle QED sense, we talk about, like a scalar field having this U1 symmetry, and the gauge field having this standard gauge redundancy like we have in electricity and magnetism. When we put things on the lattice, we're not talking about quantum fields anymore. We normally talk about creation and annihilation operators, which can have the same symmetry. One thing I struggled to understand was making this, normally in a particle context, if this were a gauge, if this were an element of the Lie group, this F would be the element of the Lie algebra. So this kind of convention here, which the author, and I also forgot to mention, all of this talk, where am I? I'm here, title page. All of this talk was based on a lecture by one of the leading fracton professors here. She's at Caltech, I believe, but she made an incredible YouTube lecture series on all these topics, and so that's where all of this comes from. But this was a particular section that I really struggled with, and other than her lectures, I couldn't find anywhere that covered this. So I didn't really understand what that meant to have, the symmetry generator be the delta function. But apparently what ends up happening by doing this is that you set things to kind of like a Z2 symmetry, where it's either the electric field can either be 1 or 0, because the charge is either there's a charge on the lattice point or there's not, and so that is where I understand this pi coming from, and these what you make of the tau z operators. Moreover, another thing that I was struggling to understand was this commutation relation between the electric field, like an external field, and the gauge field. This is kind of the only, now that I think about it, it's kind of relates to what we were talking about before, where it's, there might not be something like this if the location is different. Because if you look here, it's significant where the lattice sites are. So maybe this is related, but I was kind of struggling to understand where something called this unitary operator comes from. It was incredibly significant in that lecture series in breaking it up into particular components. When you have a Z2 symmetry, notably they're breaking up this component into the following, where you have this 1 or 0 based on your charge, and you have this integration around a particular vertex, which is either 0 or pi, again, based on your Z2 symmetry. And so this is also, this was kind of what the lecture series ended on. And let me actually show you the timestamp of what I'm talking about. It's around the 1 hour 51 mark of the second lecture in this series. This is, I believe it was in Italy, something like that. I think that's Italy. It was a summer school on topological lattice models. This is what I based this talk on. Let's see here.
Can you post the link to the?
Yeah, absolutely. Oops, what's going on here? Let's see.
The copy to the chat. You need to go to the Zoom. Okay, thanks.
Got it. Okay. Yeah, so this lecture series was incredible, but this was a particular, and if I'm, if I read it correctly, and this does in fact have some relation to this higher form symmetry business, I'd be really interested into, finding out how it's related, and moreover, I really didn't understand that, this was kind of the punchline where you make this identification with the gauge field and this with the matter field, and somehow this is exactly the toric code. I didn't exactly understand that because in the toric code there are no matter fields and gauge fields. It's just we only made that once we had eliminated the matter fields. So I'm on one hand, the whole argument that the toric code is like QED on the lattice didn't really, it wasn't really settled for me. But also, I saw, this is a very recent paper, like I think last month, and I was, kind of attracted to it because of, maybe I'm reading too much into it. But I welcome anyone to either talk now or send an email about maybe some of this. But overall, thank you, Professor, and everyone for listening and just allowing me to do this semester. Was very fun.
Okay, thanks, Jason, for a very nice talk. Any comment, questions? Maybe I'll just, the last point that you brought up, maybe I'm wondering whether you put a fermion on each lattice size, then you somehow just use a Z2 gauge field, and then you could probably do a Jordan-Bickner transformation from fermion to qubit, and I'm not sure. Maybe you would.
Okay.
Yeah. Maybe you could get this. Yeah. Or
yeah. Really.
Does
Any
it rely on that you have a fermion, or?
I didn't think so.
You just take the matter to be just abelian, just qubit from the beginning.
At the beginning, so I didn't understand where that comes from.
It could come from you start with fermion, but you do a Jordan-Bickner qubit.
Okay, yeah. Any keywords to be thrown out would definitely help because I was looking all over.
In 2D, usually Jordan-Bickner works very well in 1D. In 2D, you need to have an ordering on these fermions.
Okay.
Yeah. So, any questions or comments from other people? Okay,
so sorry, I can have a question now. I just couldn't really get the procedure of the part of integrating out. So let's say probably we can go back to toric code or something. So when you say like integrating out matter fields, I couldn't really get what actually is done in this procedure. Can you a little bit explain again or something? What's going on in integrating out matter degree of freedom?
Yeah, Jason, I think I accidentally knew you, so could you unmute yourself?
Yeah. Oh yeah, okay, there it is.
I was trying to mute myself, but it's turned out.
It looked like my video was off as well. Okay, yeah. So let's see, what was I? This particular citation helped a bit in terms of when I first read it. So let me go back to that and we can look at it together. It was a particular stack exchange. Yes, sir. Let's see.
Website.
Right.
Yeah.
Let's see here. So what does it mean when you integrate out a field from a theory?
So in this case, they're explaining the path integral, right? And
yeah.
Just integrating, really path integrating, like a matter degree of freedom, like a...
Yes, yeah, you're taking like a heavy degree of freedom versus a light degree of freedom and making like a like an effective field theory when you're only talking about one degree of freedom. But I agree. Like I struggle myself connecting that with like this lattice formulation.
Like especially Hamiltonian gauge theory. So I don't
yeah.
know what's going on here. So.
And yeah, I struggled with it as well. And the only way the only way that made me feel, because I, have a hard time moving forward if I don't understand the step behind me, was that all I'm doing right now is making an effective field theory. And so integrating out in one context and integrating out in other contexts, I'm just going to view that as an effective field theory where I'm only considering certain degrees of freedom. So I'm envisioning, let's make the identification that my matter fields are my heavy fields in like, your particle language, and my gauge fields are my light fields, and I'm only looking at my light, my low energy case or something like that. So that was the only way that made me feel comfortable with moving on. But I agree, like I can't think of a formal way to make that identification.
Would maybe just fixing the values of the matter degrees of freedom work in this case?
That's a good point, because if you fix one of them, like you're automatically inducing that it like anti-commutes or commutes with something else, so you might end up creating that zero anyway. Is that what you mean?
Maybe.
Well, usually in field theory, we do like a completing the square or something, and then bilinear fermions integrate it out easily. So I'm not sure that works, but yeah, or that making the constant works. I'm not sure how it works, but I think people are answering. I'm not sure. I would think about it.
Yeah. Same. I'm writing down everything everyone says.
So there is a paper by Levin and Gu in the condensed matter.
Okay, the braiding
Context.
statistics one.
Yeah.
Yeah, I think
They didn't integrate out. They have some duality between the spin model and the string model.
Or maybe you're talking. Is this the one you're talking about, or is it the 2005?
I posted in the chat.
Oh, okay. Right.
Yeah, so they also talk about coupling the spin model to a Z2 gauge field. So they have both gauge and spin degree of freedom. And then the next section they talk about duality between the spin model and the string model. I think they mean the gauge model. Yeah, you have to read this.
Okay.
But they.
So this is like the string net type of stuff with when.
Yeah.
Okay.
They say an important point is that the dual string degree of freedom always form closed loop. Yeah, they certify QV for the one.
Okay.
And using this correspondence, they can map the spin model to a dual string model.
Okay, so maybe thinking about things in this, I guess like string net. Okay, yeah, thank you.
Sure. Okay, any other question or comment? Okay, so thanks Jason again.
Thank you.
Yeah, you could put a thumb up or just clap. Okay, I'll stop recording.
Awesome.
Okay, and then if you figure this out, and maybe next time you could briefly comment on some of the questions that we figure out.
All right, thank you very much.
Yeah.
See you, everyone.
Yeah, so I'll end the meeting. If you'd like to speak to me, anyone like to speak with me, you can stay. I'll just stay for 5 more minutes. Okay, but